I would now like to invite Professor Purkashanian, and my apologies if I did not pronounce your name correctly. He holds the chair in energy engineering at the University of Sheffield and serves as head of the university's Energy Innovation Center. He's a general secretary of the International Flame Research Foundation and managing director of both the Translational Energy Research Center and the SAF Innovation Center. He's a member of ISCF Industrial Decarbonization Advisory Group, the Defense Supply Forum Working Group, and the Jet Zero Task Force SAF Finish Group. He was appointed OBE in the King's New Year Honours List 2023 for his outstanding contributions to net zero research and innovation. He will be presenting regarding the innovations in SAF on insights from research projects. Um, Professor Purkashanian, would you be able to switch on your video? Um,
I have, can you see me or can you hear me?
yes, I can see you and hear you.
Okay. Would you like me to upload it or you are doing it?
I would prefer if you could upload it. It would be easier to navigate. In case you prefer that I upload.
No, sure. I will do that, no problem. Can you see my presentation or?
Yes, it's just come up. I can see it in normal mode.
Okay, it's on the second screen. Sorry, let me just.
Sure. Should I present it? Happy to do that.
Sorry?
Should I present
it? There is a two screen here, so it goes onto the second screen. Let me just.
Sure. Yes, please take your time.
Okay. Let's see whether I can do it now. Okay, can you see now full screen?
Yes, we can. Thank you.
Okay, thank you very much. And good morning, good afternoon, or good evening, depends on what part of the world you are. What I will do in the next 15-20 minutes is really to look at next generation sustainable aviation fuel production pathway and look at how academic research can really accelerate SAF production. And what I'm trying to say in here that really all these innovative ideas generated from a lab, bench scale work, and lead to the demonstration plant, and finally ends up as a commercial product or a bankable product. So always looking at these next generation technology for future in terms of reducing costs, in terms of making it for more environmental friendly, is a very important part of developing new fuels or a new energy system. So as we all know, and we have heard already today, SAF is very important for decarbonization of the aviation sector. We know that, for example, mandates in UK, mandates in US, European Union, Far East, India, even area in Africa are now looking at these mandates and trying to not only implement it to decarbonize the aviation sector, but more importantly, to act as a producer, because the demand is very high. So to move to the next stage, really, let's have a look at what are the technical assessments of the novel SAF pathway. And at this moment, if you go to the market and you say you want a SAF, only options that you will have at a reasonable quantity is a HEFA. And therefore, the current state of SAF really relies on HEFA, and this is the fuel that are available and is being used. However, with HEFA, as you may know, both UK and European Union have shall we say, at some point they want to minimize the use of HEFA, and therefore there is a cap for it. And for future, HEFA will be not a major SAF producers. But as the previous speaker mentioned, then there are other options available, alcohol to jet, and there are certain technical issues that has to be resolved and optimized, but is available. You can actually make SAF from alcohol to jet, and whether it is a methanol or ethanol depends on the route that you produce, but also power to liquid. Power to liquid has great interest, interesting sort of route, because your feedstock is more or less available unlimited. And when I say unlimited, providing you have hydrogen, and this is green hydrogen, and you are capturing CO2, whether from combustion process or from direct air, you can produce fuel, SAF, using the power to liquid. And there are some other technologies coming in, and these are more of an advanced biological pathway. And we will look at these very briefly in the next 15 minutes. So why do we say HEFA, which is the existing technology, why do we say that we still need some other technologies? And one of the reasons is definitely feedstock, availability of feedstock, cost, and more importantly, the carbon footprint. So in other words, if you're using HEFA, at best, you will be replacing fossil fuel in terms of the CO2 emission by around maximum 75%, depending on the way that you produce it. And therefore, replacing jet fuel in terms of the CO2 emission, HEFA only covers part of that. But more importantly, from commercialization point of view, there are certain critical limitations. These are feedstock availability. If you consider all the feedstock available through the route that has been used at this moment, you're talking about 2.5% of the jet fuel, international jet fuel demand. If you are going for high product, look at the cost, and SAF is one of the major issues is the cost, and therefore high production cost at this moment. The best you get HEFA at the market is around $2.2 per liter, and therefore it is pretty high in comparison to the jet fuel. And more importantly, there is a competition between HEFA to use feedstock through HEFA route to produce fuel in comparison to the food production. So there's another challenge, and scaling challenge for carbon intensity goal that I mentioned before, that it doesn't replace jet fuel at 100%. So what are the technology available? Alcohol to jet, and these are the alcohol to jet pathway, methanol and ethanol. Ethanol is possibly the best route because it also have an infrastructure already set up, so you don't have to restart from the point of view of building the plant for ethanol production. And the process fundamentals, I will not mention too much because previous speakers already talked about this. But in terms of technical advantages over the HEFA or over the existing technology, you have variation in the feedstock. And you can go all the way from sugarcane, corn, and all other type of biomass into the ethanol. And more important, as I mentioned, utilization of the existing ethanol infrastructure and superior cold flow properties in comparison to HEFA, and more importantly, lower aromatic content. And I will come back to this later on, showing one example from Flight 100, why reducing aromatics in the fuel has a major impact on the contrail, on the energy density of the fuel, and therefore considered as a benefit, providing we stay within the 8% rule of the ASTM. Key challenges, therefore, is how to bring in the multiple catalyst step to increase the capital intensity, higher hydrogen requirement than conventional refining, energy-intensive distillation steps, and finally, if you do have a contaminated feedstock and flue gas, then you will end up with a catalyst deactivation, and that is an expensive process for replacement. Power to liquid, and what are the technical foundation for power to liquid, and why there is a really push, especially at European market, towards the power to liquid. If we look at the regulation mandate of the European Union, by 2050, according to that mandate, 70% of all the fuels to be used in EU should be SAF, or non-fossil fuel. And out of that 70, 50%, or in other words, 35% of the total total jet fuel used in Europe by 2050 should be power to liquid. Power to liquid has many advantages, especially in terms of carbon footprint. Is produced from providing you use renewable electricity, and this can be excess energy that can be available, solar, wind, or any other sort of renewable power, biomass, this BECCS. Water electrolyzer, whether it is PEM-based or alkaline-based. Carbon capture, whether you capture the CO2 from industrial or power generation, or whether it's a direct air capture or is a biogenic source. Carbon capture has to come from there. And then, of course, having all those three feedstock, then you go through syngas production. And once syngas is produced, you go through typical Fischer-Tropsch process. So why we are not doing power to liquid? There are many challenges at this moment. And critical technical challenge is really relates to the extremely high electricity requirement. And especially if you are using a grid, electricity generating grid, you are dealing with very expensive power, and therefore the cost of SAF produced through this route will be very high. At this moment, especially if you are using reverse motor gas shift reactor to convert CO2 to CO, because of the high energy requirement for the reverse motor gas shift reactor, you have a lower overall energy efficiency. High capital cost, because you have to involve electrolyzer, you have to involve Fischer-Tropsch, as well as of course, the reverse motor gas shift reactor, and therefore capital cost is high. And CO2 capture energy penalty and cost, especially if you are using direct air capture. At this moment, direct air capture captures CO2 at really very high cost. And scale-up challenges for catalyst manufacturing and reactor design, still some of them are on lower TRL 7 to 9 and not a bankable product. Breakthrough technologies are coming through because of these mandates that accelerates production of the SAF through power to liquid, and therefore there are a number of promising innovations that is starting to show how to deal with some of these critical technical challenges. That includes, for example, high temperature CO electrolyzer. These are, for example, companies like Fuel Cell Energy in US are now working on solid oxide electrolyzers that will provide with the CO2 CO, and also some of these structured microchannel reactors that really improves the efficiency of the Fischer-Tropper reactors. For example, companies like Green Lizard now working on advanced Fischer-Tropper reactors that pushes the conversion to well over 75%. And then we have, of course, a next generation technology that very much based on microorganisms that creating entirely a new production route. These are in very low TRL level, and but however, once it does start to produce significant amount of fuel, possibly beyond 2035 or so, there are ways that these type of process will become very important. And these are really what you do in this sort of process. You molecular engineer the jet fuel. You actually produce using the biology platform to develop a product or a fuel that is required for aircraft engine. And the main advantage is that you produce fuel that engine manufacturers want. So in other words, you produce fuel for the engine rather than what was happening before, that engine produced in order to meet the requirement for the fossil fuel-based aviation fuel. Now, finally, to look at techno-economics comparison of the next generation SAF and look at in terms of the carbon intensity as well as the production cost, you see that a conventional jet, very cheap at the moment, you're talking about $0.5, $0.6 per liter available, but carbon intensity really high. Then you go to HEFA, cost is in comparison to conventional jet is high, but lowers the carbon footprint, carbon intensity. And as you move on to the next generation technology, you see those changes that taking place in terms of cost. Costs are increasing and intensity in terms of carbon footprint changing and reducing, which is really clear indication how to move forward. And for example, if you look at power to liquid, providing you are using renewable energy, in terms of carbon intensity, you see how low it is in comparison to all other technologies. And these are the sort of area that you have to balance to see which one is best for what reaction. So I give you one example of Flight 100, where you can see, we looked at the impact of the SAF on environment, on the energy, or on the fuel efficiency. Flight 100 was a flight that was organized by the UK and US government, led by the Virgin Atlantic. They were brave enough to take the challenge and say, if this is the challenge, if using SAF at 100% on both engine is a challenge, they accept that challenge. So we worked on this process as a part of the consortium led by the Virgin Atlantic for over a year. And then we did some work in our lab, our laser diagnostics lab for APU engine, using the SAF, HEFA SAF that we were going to use in the aircraft for the flight, and looked at the measurements coming through. This is an APU engine, and we measured the emissions using the conventional facilities as well as laser diagnostics. And what is quite interesting, if you look at the right-hand side of the picture or left, you see the particle emissions. The top graph shows emissions that measured for the particulate That green line measures the particulate here, if you can see my arrow, and that is the conventional jet fuel. So it's producing, and we are measuring that. Now, at one point, if you look at this bottom, where it says the SAF 100%, when you switch over to the SAF, this is what happened to the particulate. So in other words, significant reduction, up to 70% in terms of number and 40% in terms of mass was picked up in terms of the reduction. And if you look at this graph, you see how, for example, when we added aromatic SAC to the HEFA, you start seeing increase. These blue bars shows HEFA with 12% SAC, and therefore that showed increase in the properties, in the emissions level. NOx level and other gases didn't change much, but again, if you look at very interesting data that we obtained, that when you look at fuel consumption, when you switch over from jet fuel to HEFA, the fuel consumption reduced by around 1.5 to 2%. You may say that's a very small number, but if you take that into account for all the fuels that are used at international level, that is a huge amount of fuel saving if you switch over to SAF. So in our center, we do carry out work in terms of producing SAF, around 200 liters a day, but we have a combination of the facilities for carbon capture, the next generation technologies like MCFC, in capture plant, but rotating packed bed, another type of technology, or direct air capture. We produce our own green hydrogen. We also produce the flue gas either from biomass or from gas turbine. These are the pictures of the facility available inside. And then we have a Fischer-Tropper reactor that these gases are fed into it, and therefore you end up with SAF. And there we carry out performance tests using our APU engine, aircraft engine, and if necessary, characterize the fuel for pre-screening and tier 1, tier 2 ASME type characterization. We are now working in next generation technology for SAF production that will have a major impact on the cost of SAF produced. And this is one of the projects that funded just recently by UK government, and therefore we are looking at producing SAF and at the same time capturing the CO2 from industrial processes and producing power, and if required, producing hydrogen all at the same time. And this is a technology that really proving this great potential for future. So I finish with my little comments that what are the REACH priorities? What are the research priorities? If we look at it in terms of research, I would say catalyst, catalyst, catalyst. The more you make the more improved selectivity and lifetime, the catalyst that has an improved selectivity and lifetime, you increase the efficiency, you increase the performance, and therefore reduce the cost. We are seeing every day more and more advanced electrolyzers are introduced, and therefore efficiency of these electrolyzers will have a major impact on power to liquid, because hydrogen is a major challenge. Cost of hydrogen is a major challenge for power to liquid. And finally, developing a low-cost, scalable CO2 capture technology. Direct air capture at this moment is extremely expensive, and therefore, how can you improve that? Moving to the demonstration project.
My apologies. If you could wrap in the next minute or so would be
sure. Great. That's the end of it. Yes. Scale up integrated power to liquid and establishing more poverty liquid demonstration. And finally, in terms of policy, all of these research priorities demonstration project can go ahead if the policymakers provide that certainty to the investors that SAF has a future and will be a major fuel for the future in terms of decarbonization. And that is all from me.
Thank you so much, Professor. Amparo, I will just take 5 minutes of Q&A and just one poll that we want to give. I would now like to request all our panelists to switch on their video if possible. I would just like to take a picture for our social media handles. Um, uh, would I have Mr. Parolini and Mr. Mandel with us? Mr. Mundel with us? Mr. Hewell, in case you're also here, would be great to have you. Okay, regardless, I think we'll go ahead. Oh, great. That's all of us. If you could all just smile for a moment, we'll be grateful. Thank you, gentlemen. I would now like to request everyone, the panelists, the public, in case anyone has any questions, please feel free to put it in the chat, and we will ask the panelists now. I would also like to launch a small poll for everyone. Let me know whenever my screen is visible. Yes, if you could just fill in which organization you belong to. So I'll just take this for 2 minutes or so. Very interesting results, I must say. We have quite a few academicians with us and some policymakers as well. Meanwhile, I would now like to ask questions to our panelists. There's a question from Ms. Shruti Nair saying, how does ATJ pathway compete with other pathways for SAF? ATJ pathway has a higher capex, which is also accompanied by a lot of food versus fuel debate. Mr. Monterio, this is for you, I believe, if you could take that.
Yeah, sure. First of all, let me please tackle with a personal opinion, of course, this food versus fuel debate. I do believe that this is reflect of a very European vision. And what I mean by that, of course, I don't want to create any kind of polemics here. I just would like to add that in some countries, such as if you think about the example of Brazil, this discussion doesn't apply at all. There is no competition between food versus fuel here. There is no such a way that you are displacing land or using land to produce fuel rather than food. In some cases here in Brazil, actually to produce fuel can help to improve the quality of the land and can help to improve the food production. Related to the other parts of the question, how the HJ pathway can compare with the other pathways. I mean, again, let's think about that simple framework here, advantages and disadvantages, right? First, disease technology should be proven at scale. Second, it requires some kind of higher capex when we compare, for instance, to the HEFA pathway. And in some cases, also the OPEX can be higher. And third element that is associated with the ATJ pathway, in some sense, the CI can be lower when we compare to the HEFA pathway, but it's higher when we compare to the SAF and the more alternative pathways. So that would be pretty much the main set of criteria that I can have here from the back of my head to compare these pathways, the ATJ pathways with the other ones. I don't know if did I answer your question or if you have any kind of follow-up.
Uh, Thank you. Ms. Miller, I think one more question for you. Why are HEFA and ATJ projected to be the leading pathways for SAF reduction rather than alternatives like Fischer-Tropsch and power to liquid?
Okay, if we think about the 2050, our forecast, it will be a third, right? It's not that one is predominant than the other one. It's pretty much each one will represent 33% of the share of SAF production. Surely, if we think about the reality today and how it has been evolved, it will be first half a pathway is still 90 to 90, let's say 80 to 90% of the SAF production. In the second step, it will be the HJ pathway, leverage the current infrastructure as well as the more possibility to scale. Let's say that is easier to scale. And in the third moment, there will be the alternative pathways. I have seen some studies that points that the cost to make eSAF, PTLs, and other ones are 8 to 10 times the price of the jet fuel. So if you think about an industry that is very sensitive to, let's say, to their cost, and their margins are pretty low, that's the airline industry, and at the same time, this is an industry in which the fuel costs represent 40 to 50%. It's not reasonable to think that in the short to medium term, this industry will be able to bear a cost of a fuel that is 10 times uh, 10 times the price of the fossil fuel. If we think about the eSAF, the PTLs, let's say the more alternative pathways. So that's one of the main reasons that we believe that this growth will be not as fast as the HEFA pathway and the ATJ pathway. But I'm saying here up to let's say the next 15 years, and in the decade between 2040 2050, surely PTL and eSAF and the other more alternative pathways will play an important role in the mix. You are mute, Isha.
Hi, sorry, I have one more question from Mr. Spade regarding e-fuels mandates for Europe. Sorry. Regarding the e-fuels mandates for Europe, do you foresee renewable electric growth and technology improvements sufficient to meet 2050 goals? And I would like to ask Professor Prokashanian because of his proximity to Europe and his view on this matter.
Sure. Yes, that's the target European Union has, 35% of the total energy, total jet fuel to be used from 2050 onwards has to be power to liquid. And what you have to keep in mind that these are the target, but targets also not only based on decarbonization of the aviation sector, but we also have to keep in mind energy independence and energy security. Because if you can produce your fuel within your region, that provides you with energy security. It is a challenging target. And for example, if you try to estimate how much power you need to produce that much fuel in Europe, which will cover 35% of the total fuel used in Europe, power to liquid, you're talking about at least a few percent, 4 to 5% of all the power generated in Europe. However, by 2050, Europe has a clear strategy to move forward in terms of renewable power. They have excess renewable energy in some countries already. and therefore that option is available for them. And more importantly, the price of the power to liquid is mainly depends on the cost of hydrogen and cost of power to produce hydrogen. And you are picking up CO2 from combustion process. So if the cost of hydrogen goes down to under $2 per kilogram, this is the green hydrogen, then the power to liquid, according to the World Economic Forum data, will be the most attractive fuel available to replace jet fuels.
Great. Thank you, Mr. Purkashanyan. I would urge the panelists to look at the chat because I think there are a lot of questions for Dr. Ramakumar as well. I don't think, unfortunately, we'll be able to take all the questions in person, but if you could take those on chat, we'd be grateful.